So this is an orientation to Earthdata Cloud access. Where is PACE data located? We've learned that it's in the NASA Earthdata Cloud. What does this mean? The NASA Earthdata Cloud is an AWS cloud, an Amazon Web Service cloud that's physically in Oregon. So this picture here is where PACE data is being stored and where CryoCloud essentially is being run on. This is the US West 2 region. PACE data is located in simple storage service or S3 buckets in this cloud. Ian just mentioned how it's organized a little bit differently. So PACE data is organized in these buckets, which are essentially cloud storage containers used to store and organize data. So how can I access PACE data that's in the cloud? Jeremy touched on this a little bit in his presentation. There's 3 options, 2 of them are similar. The first option is NASA Earthdata Search. That's getting data from the Earthdata Cloud. And then the second 2 are the OBDAC level 3 and 4 browser or the OBDAC file search. So those are browsers that the OBDAC, Ocean Biology DAC made. You might be familiar with the level 1 and 2 browser. That is what most people went to grab MODIS, other heritage satellite data. PACE data, this browser does not support access to PACE data. So you'll never be able to use this page to get PACE data like you might have been used to before. But the level 3 and 4 browser you can. And that looks like this, just so you guys are aware. So you can go here and press, did I lie? Oh, thank you. You go to you go to provisional and then you'll see PACE OCI. So that's one way you can get level 3, level 4. Okay, so we're gonna check out NASA Earthdata Search. So the URL is search.earthdata.nasa.gov if you wanna check it out. This changes a lot. So to get OBDAC data, you're gonna scroll down and go to Browse Data by Portal, and you'll see all the different DACs and projects. We want the Ocean Biology DAC, so don't press more info. That'll take you to the website. Just press like the icon, and that'll take you to a page that looks like this. So you can see up at the top, OBDAC. This is all of the OBDAC data that's in the cloud. So you can filter things on the left-hand side. You can filter instruments. So we want, let's say, OCI data. So that will change the search results to just be PACE OCI. And you can see here the titles of the data. So we have level 2, apparent optical properties, or AOPs. That's where remote sensing reflectance is stored. Level 1B, level 2. And what's nice about this is if you click, I didn't want to do that yet. Did I? Yes. If you click a file, you have this map on the right-hand side. And if you just, toggle over these, is it working? If you toggle over, these different data files, it shows you where the granule is located in the world, which is pretty helpful if you're looking for a specific area. So you can directly download files right here. You can press download, and it will take you, well, you have to log in, but you can download it locally to your laptop. You can do bulk download. I don't recommend downloading 56,000 PACE level 2 files to your local laptop. But that is where you can find all the data. So like I just said, you can directly download NetCDFs and run an analysis just like you would with previous ocean color data. But you might be asking, PACE data is a lot larger, right? It's hyperspectral data, they're large data cubes, and your little laptops are running out of storage. Or PACE data is so big and my laptop is having trouble processing it. The fan keeps going on, it's getting really hot, I'm scared. And you might want to process in the cloud. So lucky you now have access to CryoCloud. And like Ian said, you have access to this forever until CryoCloud goes away. Hopefully that doesn't happen. But I mean, that's super powerful that you guys will now have this tool for your research forever. So to process data in the cloud, you need what's called an elastic compute cloud, or an EC2. That is a resizable virtual machine in the cloud. It lets you run servers on demand. It's like having a computer in the cloud. CryoCloud is an Amazon EC2. This allows you to stream and analyze PACE data without it ever touching your local computer. And what I mean by stream, think of Netflix. When you stream movies and shows, you're accessing this data, running analysis on it without it ever touching your laptop. You're just doing it all in the cloud. Netflix, all the movies and shows are hosted in a cloud, and you're streaming that to your TV to watch it. What if you don't have access? So some universities are beginning to get institutional AWS accounts. Like Ian said, you can budget cloud services and proposals. And then we have a lecture on Thursday, Environments and Containers for Reusable Projects, or it's a tutorial that will go into this a little bit more. This is a great resource. This is the OpenScapes NASA Earthdata Cloud Cookbook. Highly recommend you check this out, to learn more about the cloud terminology and just learn more about cloud infrastructure. And today we're going to be using Earthaccess. So Earthaccess is this amazing Python library that people have. It's an open access Python library that anyone can contribute to, and it's a tool to search, download, and access NASA Earth science data from NASA Earthdata Cloud using just a few lines of code. It is under active development. If you see issues or run into something, you can submit issues on their GitHub. And if you want to contribute, if you start using Earthaccess a lot and have ideas of how to make things better or a new function within Earthaccess, you can contribute. So let's transition to the Jupyter Notebook. So I want everyone to go here to the code page of the PACE Hack Week website. Give me a thumbs up when you get there. Cool. Now I want you guys to download, and don't press it. If you press it, it'll look like this. I want you to right-click it and press Save. Oh, what's going on? Save link as, and just, you can name it this. Save it in your downloads. We're saving this notebook locally, and then we're going to drag it into our Cryo Cloud to open it. So that's just how we're going to open all of the tutorials this week. We find them on this page, you download them locally, and then we'll just drag them or upload them into Cryo Cloud. So let's go to Cryo Cloud. Your contents might look a little different. I have some folders of things I'm working on. You should all have this shared and shared public. I made a new folder called Hack Week 7 minutes ago. Well, a little bit longer, but let's see. It's not refreshing. Okay, anyways, I recommend you guys make a Hack Week folder. So you can do that by, how do you do that? Where's the little folder button? What am I not on? What do you mean default? This is what I want. Yeah, you can make a folder here. Usually there's an icon up here though. What, am I not in the right one?
I just want to make sure. No. I'm confused.
Me too. Anyways. You might have an icon, or you can right-click in the white space and press New Folder, and you can name it Hack Week. So I did that up here. It's empty. This is where I want you to drag that downloaded. Why is this? Or you can do File. Sorry, guys. File, open from, no. Okay, there's a button called Upload Files where you can find the notebook that you just downloaded. Here it is. Okay, give me a thumbs up when you have successfully done that. Okay, great, you guys are faster than me. Sorry about that. So go ahead and double click it to open it. If you get this notice, you can just press select. We're going to be using the Python 3 kernel for this week. And we'll go ahead and get started. So quick thumbs up if you have this notebook opened on CryoCloud. Awesome. Okay. If you have any questions or need help at any point, just raise your hand, and Ian or I will help. Okay, orientation to Earthdata Cloud access. I'm not going to read all of the text, but basically this example, we're going to use the Earthaccess Python package to search for PACE OCI products on NASA Earthdata Cloud. In short, Earthaccess helps authenticate with an Earthdata login, makes search easier, and provides a streamlined way to load data into Xarray containers. So we're going to be using Xarray a lot this week. That's another Python library that allows you to open netCDFs or multi-dimensional data. Learning objectives. At the end of this notebook, you'll know how to store your NASA Earthdata login credentials, how to use Earthaccess to search for OCI data using search filters, and how to download OCI data, but only when you need to. So for the most part, since we're on CryoCloud, we're going to be streaming most of our data, but if you need to download data for any reason, we'll show you how to do it. So, beginning of every notebook, we will import the packages used. So this is the first chunk of code we'll run. You can either press the play button right here, but I highly recommend you getting used to Shift-Enter. Shift-Enter, Shift-Enter, Shift-Enter. That will run each kernel and run the code within the code kernels. So go ahead and run that. Step 2, NASA Earthdata authentication. So this line of code right here, if you run it, it will open up a for your username and password, and that will save in a .NET RC file in your contents. It'll be hidden, so if you go to View, Show Hidden Files, you'll see it, but that is where your Earthdata username and password will be stored. So you only have to do this once, the very first time, and then going forward, when you run this, it'll just grab your username and password from that .NET-RC file, and you're good to go. So I need to look at my phone for my Earthdata login. Sorry. I deleted it because I wanted to show you in real time how to do this. Oh yeah, and if you don't know your Earthdata login at this time, that might be a problem. So hopefully you all wrote it down. Okay. Okay. Give me a thumbs up if you have successfully logged in and ran that code. Okay, so maybe half. So I'll give you a couple more minutes to maybe find or 1 more minute to find your username and password to sign in. Okay, how are we doing? Thumbs up if we're good? I'm going to go if I see majority thumbs up. Okay, I'm going to keep going. Okay, we're going to search for data. So now that we're logged into Earthdata, we're going to use the earthaccess.searchDatasets function. So we're going to run this, and we're going to use a search filter for instrument. So we want all of the data files where the instrument equals OCI. So you can go ahead and run this, right? Shift-Enter. It ran. You can also, I don't know if Ian mentioned this, but to the left here, when a code kernel is running, it's an asterisk, and then when it's done, it shows a number. So you can always tell when it's done running if it's a number. And then also, my screen's a little enlarged, but in the right-hand corner, you should see this open circle. When this is open, it means it's idle, nothing's running. When it's solid, that means your code is running. So those are 2 ways to check when your kernels are actively running code. So next is this little for loop. For every item in the results, we want to print the item summary, which gives the short name, which is another way to say all of the PACE OCI file names within Earthdata Cloud. So you can see we have level 1B, level 2, level 3B. All of the data is printed here. So you can see like we have some level 3 Moana, we have some level 3 land vegetation indices. So you can see what's available just by running this command. Now we'll use the search data function. Before we used search data sets, now we're going to use search data to find granules within a collection. So we'll use the short name PACE OCI Level 2 BGC, that stands for biogeochemical products. And we're going to just do the first one, so count equals 1. And then we want to print the length of that result. So run that, and the length should be 1 because we're only grabbing the first file in level 2 BGC data. Okay. So we can refine that search by passing more parameters that maybe describe the spatiotemporal domain of our use case. So we can use the temporal parameter, bounding box, and cloud cover. So here we're using search data again. We're finding PACE OCI level 2 BGC data, but we want the T-span to be between July 1st and July 31st of last year, 2024. And we want the bounding box to be this location, which actually encompasses the Chesapeake Bay on the east coast of the US. And we want 0 to 50% cloud cover, so 50% or less cloud cover data. So we can go ahead and define our T-span, B-box, and clouds, and then run the search data. Now we have 4 results. So there are 4 level 2 BGC data files from that month in July, overlapping that bounding box with 50% lesser clouds. Cool? Okay. So displaying the results shows the direct link. So if you run this right here, results with the, this is indexing the first, oh, go ahead.
Quick question.
Yeah.
How can I know which parameters are supported for a specific data?
Like a specific data file?
Yeah, for a file.
You can put in granule, I believe. What is the search filter to get a specific data file?
You mean like what are my options that I can use as a function?
Yeah.
Yeah. Well, so you would need to go to help or anything. So and if you hover over search data and like right click, does it give you or tab? What is it? So you can get help on the file. Earthaccess has a read the docs page. So it's get that update.
People check cursor at the end of data and press shift and add it to the down.
Shift it. Is that what it is?
There is a read the docs. If you Google NASA Earthaccess, you can find the read the docs. I will say it's not totally well documented because it's under development, but there's some how-tos, search for data using filters. There's some more examples which shows you other search filters to get what you're looking for. I hope that helps. Yeah. Yep. Yep.
Invoice is it our phone?
Is what? Sorry.
Invoice refer back to you whether that you document. Yeah, invoice. E-box.
Oh, B-box, bounding box. So it's this lat long. What is it north, south?
West, south,
Long lat, long lat.
west, south, east, north. West, south, east, north. West, south.
Got it. I maybe should make that note in here. West, south, east, north. Okay, so running results, indexing the first file, it pops up a direct link. So you can press this. Well, okay. You can press that, and if you're logged in, it will take you to a download link where you can download it directly. So that's one way to download files directly to your local laptop. So if you're running the notebook locally, this may be of use. However, in the next section, we'll see how to download all the results with one command. So that's just how you can do that. So now let's open level 2 data. So we're going to open a couple granules using Xarray. The Earthaccess.open function is used when you want to directly read bytes from a remote file system. So when you want to stream data, essentially, and when you don't want to download a whole file. So we're going to run this line of code, Earthaccess.open, the results of what we searched for before. So this could take just a few seconds, but you can see here that 4 out of 4, the 4 granules that I searched for before, have been opened or found. We saved this as paths, so we can go ahead and run paths to see the file names on our remote system. So you can see it's a file-like object S3 file system. It's called the OB Cumulus Prod Public. That is the S3 bucket where these paste data files are located in the AWS Earthdata Cloud. And here you can see the names of each netCDF. So let's open the first one. So we're indexing the first paths. We're doing Xarray. I read in Xarray as XR. So we're going to do xr.open dataset of the first file. So if you run that, you'll get an output of an Xarray dataset. You'll notice that this Xarray dataset has nothing but attributes. So it has like the words, dimensions, coordinates, data variables, but you can't expand them. You can only expand attributes, and this just gives you more information on how the data was processed and some credits. So we're going to use something called xr.openDataTree, which is a newish function within Xarray dataset, which makes it easier to open netCDFs that have groups within the files. So if you run xr.openDataTree, then you see a new group here called groups. And if you expand that, you can see that there's 5 groups. There's sensor band parameters, which has all of the variables within that sensor band parameter group. It has scanline attributes. It has geophysical data, which is the data that scientists that I'm after. Navigation data, so the lat-long values, and then processing control. So we can merge all of the variables from those 5 groups by running xr.merge, getting the values from the data tree and creating a new Xarray data set. So if you run that line, now you have an Xarray data set, and you have all of the 31 variables that were in each group in one data set. Any questions on that? So data tree is what you want for level 2 data when you have these hierarchical groups within your netCDF. Okay, so you can see the variables here. We have all of them. We have the biogeochemical ones right there. So let's do a quick plot of chlorophyll A. So you can call the data set, call the chlorophyll A variable, .plot, and the Vmax is the highest value of chlorophyll. So we just set it at 5. If you run that, you'll see a quick plot of the granule that we found. The Chesapeake Bay is right here. So this file, it's not going to be just the Chesapeake Bay bounding box. It's any files that overlap that bounding box. So this is the entire level 2 granule symbolized by chlorophyll A concentration. We can plot so you can see on the Y and X axes, we have pixels per line and then number of lines. If we plot with lat long, we can project the data onto a grid. So you can go ahead and do set chords. This is an Xarray function. Set the chords as longitude and latitude, and then plot it again, declaring x equals longitude, y equals latitude. And then when you plot it, you'll get latitude and longitude on the y and x axes, and it's projected a little bit to fit the coordinate system. Cool? Any questions? Thumbs up if you have a chlorophyll plot in your notebook. Yay! Cool. Okay, and if we want to get fancy, we can add the coastline. So super easy. If you want to make like a publishable quality figure, you can play around with Cartopy. That's what, how did I define it? CR, CC, anyways, yeah, Cartopy is the Python package that allows you to add grid lines and coastlines. I guess not grid lines, just the coastlines. Okay, let's open level 3 mapped data. So level 3 mapped are global data. We're going to be using the Earthaccess.search data function again. This is our T-span, so our temporal parameter we'll call T-span. So we're looking for level 3 data from April 12th to April 24th of 2024. We want PACE OCI level 3 M chlorophyll. And here, we can do the granule name as an argument that accepts strings with the wildcard. So we can use this to distinguish day, because with level 3 map files, you can get daily, you can get 8-day composites, and you can get monthly composites. So we're just wanting day composites. And we also want the 0.1 degree. It comes in 4 kilometers, 0.1, and anyone know the last one?
It varies. I think it varies a little bit.
Okay, I forget. There's 3 options for chlorophyll data. Okay, so let's run that. So we're going to do earthaccess.search data and then earthaccess.open. And you'll see it should start loading. Also, I think Private Cloud is a little bit slow when we have 50 people doing exactly the same thing. So if it's a little slower than usual, that's why. But you should have 13 level 3 map files being opened. Okay? So level 3 map files do not have groups, so we don't need to use xarray.datatree. We can simply use xarray.dataset. So we can open this, and you can see lat, long, and the data variables, chlorophyll A. Palette is something related to RGB. It automatically comes in the chlorophyll A data file, but we're interested in the chlorophyll A variable. Okay, so because level 3 map variables have lat long coordinates, we can stack multiple granules along a new dimension that corresponds to time. So instead of xr.open dataset, we can use xr.open mf dataset. MF stands for multiple files. So if you go down to the next chunk of code, it's doing xr.open mf dataset of all 13 files. So paths is all 13 files that we opened. Combine equals nested, combines the files according to the shape of the array. And then concatenate dimension, we're going to use the date dimension. So if we run that, it opens up a new data set. And you can see in the dimensions, we have a new dimension called date. And it corresponds to the 13 different data files collected on different dates. So a common reason to generate a single data set from multiple daily images is to create a composite. So let's compare the map from a single day. So if you run this chunk of code, this is logging the chlorophyll A variable, it's updating the attributes to update it on the color bar, and it's plotting the first date. So it's selecting date equals 0, that's the first date of the 13 files, and it's using this really nice green to blue color palette. And this is what we see. So this is a global file of 1 day. You can see there's a lot of gaps from orbits and clouds. So if we want to add more data to this, we can take the mean of all 13 dates. So take mean chlorophyll of every single pixel from all 13 dates and run that. And we should see a more filled out map. So this is an average of 13 dates between the April dates that we searched for before. Any questions on this? Yes?
This is global map.
This is what?
Global.
Yeah. Mm-hmm.
Global
Yep, level 3 map files are global files.
So apart of probability, you have another variable in this set data,
Mhm.
another variable.
So this, we just searched for the chlorophyll A level 3 map file. So it's only the chlorophyll A variable, but you can search for RS, level 3 map RS.
I saw this also carbon. Carbon, which variable is used for carbon?
Are you talking about this?
No, at the first,
When you list all the different.
Oh, up at the top? Hmm?
Carbon, the hard list of topics, the long list of short names.
Right. So here's all, yeah. Where's chlorophyll?
It's at the very top.
Yeah, I grabbed this one.
But carbon isn't a
But carbon is an option. You can call this to get phytoplankton carbon. Phytoplankton carbon. Yeah. This is particulate organic carbon, POC. Okay, how am I on time? I'm 7 minutes over, aren't I? When do you go, Karina? Okay, good. Okay, last section. So let's say you want to download a couple granules. There is a function within Earthaccess called earthaccess.download. Use to copy files onto a file system local to the machine executing the code, aka it downloads it to your laptop. So we're going to search the same way we've been searching. So we're going to, like we did with the level 2 file, earthaccess.searchdata, paste OCI level 2 BGC, using the same tspan bounding box. I don't want that. I want up down here. Sorry, took me back up there. Okay, same tspan bounding box cloud cover. So it's searching for it, and then instead of earthaccess.open, we're going to use earthaccess.download. That's going to download all, I think it was four results for level 2 in a folder called data in our local directory. So if you run this, and I lied, this doesn't download data directly to your laptop. This downloads data directly to CryoCloud. So this is where you might want to be careful if you do earthaccess.download. You could be storing a lot of data on CryoCloud. From here, then you could do an additional step to get it to your laptop. But when you run that, you should see a new folder called data with the 5 data granules. I thought it was 4, but anyways. And then you can open that up, that locally saved file using Xarray as well. So you can do open data tree on the first paths, which is opening up this file that is stored locally in CryoCloud in your data folder. And then, like, if you want to download it directly to your laptop, you can right-click and press download, and that downloads it to your local laptop. And that is it. So any questions on anything we just went over? We're going to be using Earthaccess in pretty much almost every tutorial that we use this week. So really, this is like your main gateway to Earth data, NASA Earth data. Yeah, go ahead.
Yeah, I have an error with the optimal Earthaccess, but I don't know why.
You got an error?
Yes.
Might be James, could you take a look? If you, yeah. Correct me if I'm wrong, Earth data only works for an hour, the credentials, or is that's okay, never mind.
Errors are going to happen a lot. Errors are in red. Errors are learning experience. We call it failing forward. So when you get an error, feel free to share, talk about it, don't be scared. Read the message, share your experience. If you have that error, somebody else is going to have that error. It happens. Errors happen. We love that. Okay. Like public service announcement.
Go ahead.
I have a question. When you download the data, do you download the data defined in the bounding box only, or the full data set?
Full data set. It's
Okay.
full data,
Focus on the bounding?
yeah, it's what overlaps the bounding box. So full data granules that have data somewhere within that bounding box. No, no, not with Earthaccess. There's other ways we could talk about to crop data.
And so one of the important things that we're learning, and you know, we're not dumping everything on you, but since you asked the question, you know, when you used Earthaccess and Xrd to stream the data from a bucket, so we didn't download it, you just streamed it from a bucket. When you are doing that, it only asks for the data you actually use. So it's not, if you were to plot something that was, you know, if you said like, well, I want to narrow down my window and only plot a little bit of this global map, it doesn't ever touch the rest of the data. It never brings it to your instance. It can find just that those coordinates and copy those over to you. So there's a lot of the times that we start thinking like, I need to manage my data use very carefully. And in fact, you can free yourself from that a little bit and let Xrd and the backends that know how to deal with how the data is divided up do that for you. So just kind of select the data you want and plot it, and hopefully it will all merrily roll along.
Yeah, I'm following what he's saying. When you stream in that subset, if for some reason you did need to save that subset locally, you would do Xarray, so like .2, that's
Yeah.
or whatever. And then you're saving only the data that you just loaded. Although I think for a lot of what I'm doing, like if I'm doing like a machine learning kind of thing, I don't want to be saving all that data locally. I want it to like go grab the bit I want, do the thing, now grab another bit, do the thing, so that I'm never let down with it.
Any other questions?
Like there's another data variable called head.
Do you know?
I never use it. We're going to do the visualization after this. There's color palettes with Python, you know, and Matplotlib. So yeah, I never use the default palette. I'm not. Yeah.
It's a mapping of suggested colors for random visualization. If you ever use the CDAS system like the desktop that OLAP produces, it uses that information to make pictures, so we have a repeatable color scheme that we use. That will be green is your stereo, I think. Use your own colors.
Yep.
And the cloud coverage filter, is this applied to the full data set or a subset?
What do you mean by subset? It's applied
Within the bounding box, or is it the full data set?
full data set, full granule. Yeah.
Is it not possible to manipulate with only the bounding?
I don't think
Not
so.
if you're querying to the data object. I mean, you could write code, of course,
Yeah,
to
of course.
filter based on the cloud map
Just
and all that.
just think about the everything level there.
Yeah, because that's not in, there's no way that all that cloud server stuff is based on metadata in the catalog, and they can't keep as metadata how much cloud coverage over, a small metadata.
That's not shit.